Suppose you're given y equals to x minus ln of x. Question is, find intervals where graph is concave up or down. And also find inflection points. If there is any. Let's try this question. Alright, concave up or down, what does it have to do with? Second derivative, so we have to differentiate twice. If you differentiate once, it's 1 minus 1 over x. If you differentiate again, it's 0 minus 1 over x squared. Now it's important to know the domain for this function. So what's the domain? Are you allowed to have negative numbers in log? No. Are you allowed to have 0 inside log? What's log of 0? Let's think about it this way. If log of 0 was some value x, you can exponentiate both sides. So you're looking for the case where some exponential function gives you 0. Is that possible? No, the exponential graph of the exponential function is like this. It never passes through the x-axis. It doesn't have any x-intercept, so it's impossible. So log of 0 doesn't exist. So whenever you're talking about logarithmic functions, your x cannot be negative and it cannot be 0. The domain is what? 0 to infinity. As long as you're plugging in positive values into log, that's okay. Alright, so if domain is 0 to infinity, what do you see here? Y double prime is? Since this is negative 1 over x squared, if x is any positive value, see, x is the input of this function, so when you say domain is 0 to infinity, this x can only be a positive value. Positive squared is positive, so overall, what's the sign of this thing? It's negative, right? If it's always negative on the domain, what do you know? Concave up or concave down? Concave down. Something is pushing from below. Concave down. On 0 to infinity. Now, is there any change in concavity? Is there any change in concavity? No, there is no change in concavity. So is there an inflection point? No, no inflection. Okay. So we should add that there's no inflection. Okay, let me give you another example since that one turned out to have no inflection point. It was always concave down. Let's try another one with x times e to the negative x. Let's try to answer the same kind of question. Now, what's the domain this time? Exponential functions. Are you allowed to plug in negative values into e? E to the negative 3. Does this make sense? E is what? 2.7 something, right? And negative exponent means what? 1 over. So you're dividing 1 by some positive value. Can you do this? Yes. So there's no problem with plugging in negative values into E. So what's the domain then? What's the domain? All real numbers. Any value is the domain. So we have to consider this question on all real numbers. Since we're talking about the concavity, let's find the derivative. First derivative is you have to use the product rule and then chain rule. So x prime e to the negative x plus x times e to the negative x prime. If you differentiate x, you get 1. And if you differentiate e to the negative x is a nested function inside the exponential function. So you have to pull the inside function outside and differentiate. Well, the outside function is e to the x. E to the x differentiates as e to the x is unchanged. So you have e to the negative x unchanged, but the inside function has to be pulled out and differentiated, which gives you negative 1. Derivative of negative x is negative 1. Okay. And therefore you have e to the negative x plus, actually minus, x times e to the negative x, which is good enough, but since we are trying to do something more with the derivative, anytime you have to do something more with the derivative or second derivative, you always want to simplify it as much as you can before going to the next stage. Okay? And I see that e to the negative x is a common factor for both. I'm going to factor out the e to the negative x. What's left if I take the e to the negative x away from the first term? 1. 1 is left. And from the second one, what's left? Negative x. So 1 minus x is left after I take the e to the negative x away. Okay. Now, y double prime, which means I have to differentiate the y prime. It requires another use of the product rule. This gives you negative 1 times e to the negative x. We already did this once. It was e to the x times negative 1. So and this time if I pull the e to the negative x out, I have negative 1 from the first one, and it's negative 1 times 1, which is negative 1. Negative 1 times negative x, which is plus x. So I get x minus 2 e to the negative x is my second derivative. Okay. Now we have to figure out the sign of y double prime, because we know that when y double prime is positive, it's concave up. If this is negative, it's concave down. How do we do that? We first put the number line, mark the point where y double prime is equal to 0. When is this equal to 0? The first. Can exponential functions ever become 0? No, never. So the only way that this can be 0 is when this part becomes 0. When is this 0? When x is equal to 2. So 2 is the only place where y double prime becomes 0. So you want to mark that point on the number line, and then you want to pick a test point after and also before, and plug it into y double prime to figure out what's the sign of the second derivative in this interval, and also the sign in this interval. Okay? We know that signs can change only if the function has a sudden discontinuity, or the function is undefined at that point, or it passes through the x-axis. That's only time when a function can change its sign. Since this is continuous and defined everywhere, the only way that it can change its sign is when it's going through a tube. So if I test the value of the y double prime at 1 and find that it's negative, then it has to be negative for the entire interval, because it's not allowed to change signs at all before you hit 2. So that's the idea. You use test points if you know that signs cannot change in the inside the interval. Okay? So let's plug in 1. What happens if you plug in 1? What's y double prime when x is equal to 1? That's 1 minus 2 e to the negative 1. 1 minus 2 is negative 1. And I don't know the value of e to the negative 1, but definitely e to the negative 1 means something over e. So you're dividing a negative value by a positive value, so it's negative. So we know that this is negative. Now if we do the same thing for the x value 3, as 3 minus 2 e to the negative 3, which is again 1 over negative exponent means 1, it goes down into the denominator. So you're again dividing a positive value by some other positive value, so this is positive. This is positive here. And that pretty much settles all the questions that we had about this function. So what's the answer then? Is concave up where? Concave, so answer is concave up on where? To the infinity. And it's concave down? Negative infinity to 2. So before 2, the value of the second derivative is negative, therefore the original function is concave down. Now, is there a change in concavity? Yes. So at 2, there should be an inflection point, right? Now, inflection point is a point on the graph. Therefore, when you're asked for inflection points, then you should not only just find the x value, but you should also find the y value. That goes for the relative maximum and relative minimum also. In some cases, I will just say find the x value of the inflection point, or figure out when you get an inflection point. That's another way for me to ask just the x value. Yes?
The inflection point is only found from the second derivative?
Yes. Inflection point is a point where you have change in concavity. So yeah, it has to be obtained from the second derivative. Even if the second derivative is 0, sometimes you may have plus 0 and then plus again. In that case, there's no change in concavity. In that case, this won't be an inflection point. We say this is an inflection point only because before 2 it was concave down, and after 2 it's concave up.
Looking at the first derivative when we're doing the test point decrease.
Right. So we can do a similar thing for the first derivative. In that case, the first derivative, if there's a change in increasing and decreasing, then it will give you an extrema. Okay? Yeah. And such a process is called the first derivative test. Yes?
So just because you find the zeros of the second derivative doesn't mean they're points of inflection, it's just possible points of inflection?
Yeah, that's a great question. Yeah. So again, I want to repeat myself. Just because the second derivative is equal to 0, that does not guarantee that you have an inflection point. Same thing goes for the first derivative. Just because the first derivative is equal to 0, that doesn't mean that you have an extrema at that point. Only if there's a change in signs, you have such interesting points. Okay? All right. So now let's figure out the value of the y when x is equal to 2, because we know that that's when you have an inflection point. When you plug in 2, it's 2 is plugged in here, so it's 2 times e to the negative 2. You can just leave it like this, but I kind of like to use the negative as to put it in the denominator. But it's optional. You can write it like this, or write it like this. It doesn't matter. Okay. So you have 2 over e squared as the y value for x equals to 2. That means you have an inflection point at 2 comma 2 over e squared. So that's the final answer.